Now let's look at photodetectors and photovoltaics. Both of these devices are p-n junctions, and to understand what happens, we need to look at what happens when light shines onto a p-n junction. Let's draw out a p-n junction. We can draw an unbiased one. I'll put the p side and the n side, and we can identify the depletion region in the center. Let's imagine that light is shining directly onto the depletion region. It creates an electron in a hole, and because they're both within an electric field, the electron will go one way and the hole will go the other way, and they'll be separated by this built-in electric field. And those carriers, the electron going towards the n side and the hole going towards the p side, are contributing to a reverse current which will be picked up in the external circuit, and that can be used as our photo-generated current. Now let's think about what happens if the photon instead hits somewhere outside the depletion region. We're still going to create an electron-hole pair, but now there's no electric field pushing them around. The hole in the n side will diffuse around, and if it manages to diffuse into the depletion region, it will be swept across by the built-in electric field, and it will contribute to the external current. The electron won't do anything because even if it did make it to the depletion region, the electric field is in the wrong direction. So it's the minority carrier which can contribute to the reverse current in the p-n junction, and therefore contribute to the external current that we're picking up from the photogeneration of these carriers. Similarly, in the p side, it's the electron that can diffuse, and if it makes it to the depletion region, we're going to create some drift current. So light produces a reverse current. The question is, how far away from the p-n junction can we still capture these carriers? And that distance is just the order of Lp or Ln, the minority carrier diffusion length. If we're within approximately Lp or Ln, then there's a good chance that the carrier will actually make it to the depletion region. But if we're outside of that distance, then the carriers here, created here by photogeneration away from the junction, will diffuse around and eventually recombine, and we won't be able to generate any current out of those carriers. This modifies the IV curve of the p-n junction. If we have an IV curve that looks like this in the dark, then in the light we're generating an additional reverse current. So we're going to shift this down, and this point here is Ig. It's the photo current. And of course that depends on the intensity of light. So for a given amount of light we're going to have a given Ig. As we turn the light up, this curve will shift down more. Let's look at this region here. In this region of the IV curve of this illuminated p-n junction, you can see that the voltage and the current are in opposite directions. Here V is greater than 0 and I is less than 0. So the product IV, the power IV, is negative. That means that in this region we are generating power. So this region corresponds to a photovoltaic. We're generating power. And in order to act as a photovoltaic, you have to be operating somewhere in this region. It's called the fourth quadrant. The quadrants go first, second, third and fourth, like this. If we take that same p-n junction and we sit somewhere here, for example at a reverse bias, then in the dark we'll get a small current flowing. Once we turn the light on, we'll get a large current flowing, and the change in current is what we can detect. So to be a photodetector or a photodiode, you have to operate somewhere in the third quadrant so that you can apply a reverse voltage and have a small current flowing through in the dark, but a much larger current flowing through when you shine the light. So in this case we're not generating power, we're actually consuming power, but we have a very sensitive detector of light because the ratio between this point and this point can be very large, especially if you design your PN junction to have a very small reverse current here. We know the size of this is I0 from the ideal diode equation, and if we choose our device parameters properly we can have a very small I0, and therefore when the light shines we have hundreds or thousands of times more current flowing through, which makes for a very sensitive photodetector.